Hello, everyone. So this time we want to start chapter 9, relations and functions. And we want to start with 9.1, which is about relations and their properties. Yeah, relations and their properties. So I think you are familiar with the concept of functions, right? So what is a function? A function is a rule that assigns exactly one output to every input. So basically, a function deals with two sets called domain and range, and some pairs where in each pair, the first coordinate represents the input and the second coordinate represents the output. Now, and we know that for functions, we cannot have like two different outputs for the same input. But let's say if we ignore this restriction and just think about set of pairs where like the first coordinate comes from one specific set and second coordinate comes from one specific set. So in other words, a generalization for functions, then that is called a relation from one set to another. So we want to start with the concept of relations, which is a generalization of functions. We don't have the restriction that, having exactly one output for every input. So we remove that restriction and we define relations and certain types of relations, and then we'll get to the topic of functions later. So let's start with the definition. Let A and B be two sets. A binary relation. Okay, let me check whether, okay, yeah. A binary relation is a subset of A cross B. Cartesian product of A and B. In other words, a relation is a subset of set of all pairs A and B, where A comes from a set A and B comes from a set B. So let's look at an example. Let A equals, let's say, for example, 1, 2, 4, and B equals, let's say, 4 and 6. So then A cross B, what will be A cross B? A cross B means the set of all pairs A and B, where A comes from A and B comes from B. Now this is equal to like 1 and 4, and then 1 and 6, and then 2 and 4, and then 2 and 6, and then 4 and 4, and then 4 and 6, right? So this notation A cross B, again, like I said, it's called Cartesian product of A and B, is a set of all pairs where the first coordinate comes from the first set and second coordinate comes from the second set. Now, how many elements would I have in the set A cross B? Well, in A, I have 3 elements. In B, I have 2 elements. So in total, I would have, by product rule, I would have 6 elements. And those elements are like 1 and 4, 1 and 6, 2 and 4, 2 and 6, 4 and 4, and 4 and 6. Okay, so then this is A cross B. Now a relation is a subset of this set. So set For example, R1 equals, let's say 1 and 4, 1 and 6, 4 and 4. This is a relation from A to B. Because as long as I have a subset of this set, I have a relation from A to B. So this is, of course, a subset of A cross B. So it's a relation from A to B. So this is, for example, not considered as a function, as you know, because if you think of 1 as an input, then we are not allowed to have two different outputs for a single input if we want to have a function. So here we have 1 and 4 and 1 and 6. So this is not considered as a function, but it is a relation. So that's why I said a relation is a generalization for a function. So this is one relation from A to B. Of course, we can have many more relations from A to B. R2 equals, let's say the set containing only 2 and 6. This is also a relation from A to B. It's a set with only one element, but it's a subset of A cross B. So this is also a relation from A to B. Or another subset of A cross B, and therefore another relation. You could consider, let's say, R3 equals empty set. This is also a relation from A to B because it says empty set is a subset of every set, and therefore is a subset of A cross B, and therefore it is also a relation from A to B. Or more, any. So how many relations can we have here? Well, this A cross B is a set with 6 elements here, and therefore 2 to power 6. So in total, A cross B has 2 to power 6 subsets, right? We know that a set with n elements has 2 to power n subsets. Thus, there are 2 to power 6 relations from A to B. Okay, so notation, one notation that we use is that if A and B belongs to R for a relation R, then we write ARB and if A and B does not belong to R, then we write ARB. Then we say A and B are not in relation, meaning that A and B does not belong to R. Okay, so another convention is that we say a relation on a set A. So we define a relation from one set to another. But when we say relation on a set, a relation on a set A is, or means, let me say, means a relation from A to A itself. So for example, if A is 1 and 3, so then A cross A would be what? So first of all, it would have 4 elements because A has 2 elements. So A cross A would be 1 and 1 and 1 and 3. and 3 and 1 and 3 and 3. And therefore, A cross A would have how many subsets? It would have 2 to the power 4, 16 subsets. Therefore, we can define 16 relations on A, because relation on A means a relation from A to A, which means a subset of A cross A. Therefore, here A cross A has 16 subsets, therefore has 16, there are 16 relations on A. So then this, and let's say R equals 1 and 1, and let's say 3 and 1 is a relation on A. Okay, let's look at another example. Let A be the set of all people in the world. People in the world. Define the relation R as follows. So let's say we say A or B if A is the father of B. Okay, so this is a relation on the set A, which is defined as set of all people in the world. Okay, so if I want to list the elements of this set, so let's say, for example, R equals, let's say, so A, I could say the set of all living people, just. Okay, so we could say any person and his son, right? So let's say, for example, person number 1 and person number 1's son. Similarly, person number 2 and person number 2's son. And so on. So this relation consists of all pairs where the first coordinate is a father and the second coordinate is his son. Okay, so as long as a person is a father of someone, has become a father, if a person has become a father, then him and his son or, and also it could be daughter. So let's say, just say A is a father of B. So person number 1's, let's say, child. The first coordinate has to be male because it's a father of someone. But the second one says A is a father of B. So B could be whether his daughter or his son. So first person number 1's child, person number 2 and person number 2's child. And so. So the first coordinate is always a male because it's father of someone. And the second coordinate is that person's child, whether daughter or son. And if a person has more than one kid, so that person could appear in more than one pair, because let's say if one person has one son and one daughter, so one time he appears as the first coordinate, the second coordinate is his son, and the second pair, again, he appears as the first coordinate and the second coordinate is his daughter, for example, and so on. Okay. So this is one relation. Another example, let's say R, let's say A equals the set of integers. Define R, define the relation R on A as follows. A R B if A is less than or equal to B. So if A is less than or equal to B, then A comma B will be in the relation. If A is not less than or equal to B, then A comma B will not be in this relation. So what are the elements of this relation? So if I want to list the elements of this relation, for example, 0. If the first coordinate is 0, then now if this, according to the definition of the relation, because by definition, see, I'm allowed to define any relation that I want, right? So as long as I have a subset of A cross A, I have a relation on A. Now, in this example, I'm defining the relation R as the set of all pairs where the first coordinate is less than or equal to the second coordinate. Another notation for this is we say A, R, B means A and B belongs to R. If what happens if A is less than or equal to B? That's according to the definition of this relation. Well, this is how I define this relation, but of course I could define the relation in other ways. You'll see more examples, right? So this is just one way to define a relation on a set A. Now, if I want to list few elements of this relation, so this relation, A and B belongs to R if A is less than or equal to B. So let's say if the first coordinate is 0, then which pairs will be included in R? If the second coordinate, according to this relation, second coordinate must be bigger than or equal to the first coordinate. So second coordinate must be bigger than or equal to 0. So it could be 0 itself, or 0 and 1, or 0 and 2, right? Or if the first coordinate, for example, is 1, then the second coordinate could be also 1 or 2. Or for example, because I'm defining A to be Z, so first coordinate is allowed to be -1 as well. So for example, if the first coordinate is -1, then the second coordinate could be -1 again. Then the second coordinate could be -1, or the second coordinate could be, for example, 0 or 1, and so on, right? So let me add part B. For example, is 3 and 5. Or if it does 3 and 5 belong to R? So the answer is yes, because 3 is less than or equal to 5. As long as I have a pair where the first coordinate is less than or equal to the second coordinate for this specific type of relation, then I can say that A comma B belongs to R. What about, for example, 3 and 2? Can we say that this belongs to R? The answer is no, right? Because 3 is not less than or equal to 2. 3 is bigger than 2. It's not less than or equal to 2. So 3 and 2 does not belong to R, but 3 and 5 belongs to R. Okay, so this is another type of relation. Let me give you another example. Again, let A equals Z. For this one, let's say I will define A to be N. Define R as follows. ARB is in relation with B if A divides B. This is also another important type of relation. And it appears in many examples and also exercises in your book. So in this relation, we are defining it in a way that A comma B belongs to R if the first coordinate A divides the second coordinate B. Divides, as you know, means it's a factor of. If the first coordinate is a factor of a second coordinate, then we say A comma B belongs to R. Otherwise, we say A comma B does not belong to R. So for example, 1 and 3. Does it belong to R? One and 3 belongs to R because 1 divides 3, right? 3 can be written as 1 times 3, right? So that means 1 divides 3, and therefore 1 and 3 belongs to R. What about 2 and 3? 2 and 3 does not belong to R because, you know, there is no number K such that 3 is equal to 2K. Because when can I say that 2 divides 3? If 3 could be written as 2 times some number K, then I can say that 2 divides 3. But 3 cannot be written as 2K for any integer K. Because if 3 is 2K, K would be 3 over 2, which is not an integer. Therefore, 2 does not divide 3, and 2 does not divide 3 means 2 and 3 does not belong to R. Because again, for A and B, in order to be able to say A and B belongs to R, we need to have A divides B. If A does not divide B, then A and B, A comma B, does not belong to R. Another example, let's say I can set A to be set of all real numbers. So this R is the set of all real numbers, but this R is just the relation. So define the relation R as follows. A R B if B is equal to A plus 1. In other words, R is equal to the set of all pairs of the form A and B. So A R B is another notation for A and B belongs to R. So A and B belongs to R, or R contains A and B. If what happens? If B is equal to A plus 1. So all pairs of the form A and B where B equals A plus 1 are contained in this relation R. So, you know, this is a function because, you know, for every input, we have exactly one output, B, which is A plus 1. And you're familiar with the graph, right? So graph of this relation. A plus 1, right? So this is the line Y equals X plus 1, right? Because here the Y coordinate or second coordinate is the first coordinate plus 1. So if I want to sketch the graph, I need to sketch the graph of Y equals X plus 1. And then any point on this graph is of the form A comma A plus 1, where A is some real number. And this point here, for example, is 0 and 1, right? This point could be 1 and 2, and so on. All right, now we can mention some specific types of relations, specific types of relations. So definition, a relation R is called reflexive. There's a relation R on a set A. On a set A is called reflexive. If the pair A and A belongs to R for every A in A. The next definition, a relation R on a set A is called symmetric. If whenever A and B belongs to R, then B and A also belongs to R. Okay, so symmetric, when we say symmetric, if A and B belongs to R, implies that B and A also belongs to R. So it must be symmetric. A and B belongs to R must imply B and A belongs to R. So then we call the relation symmetric. And then antisymmetric, a relation R on a set A is called antisymmetric. If whenever A and B belongs to R and B and A belongs to R, then A equals B. In other words, if A and B belongs to R and A not equal to B, we must have B and A does not belong to R. So antisymmetric, from the name, you could guess that, it means that if A and B is in R, then B and A should not be in R. That's the opposite of symmetric, because in symmetric, we said whenever A and B is in R, then B and A also must be in R. So opposite of this, or antisymmetric, we could expect that if A and B is in R, then B and A should not be in R. But if we make that as the definition, there is a small issue, because what about A and A itself? Is A and A itself allowed to be in R? No, yes, we can have A and A in R, and still we can have an antisymmetric relation. So in order to exclude the case of, for example, A and A, because we have no problem with having A and A in our antisymmetric relation, we just don't want A and B and A, both of them, to be in the relation if A and B are distinct elements. So to solve this issue, we could say that if A and B is in R and A is not equal to B, then B and A should not be in R. For example, if 2 and 3 is in R, in an antisymmetric relation, then 3 and 2 should not be in R, because 2 and 3 are not the same, right? If 2 and 3 is in R, then 3 and 2 must not be in R. Or if, for example, 1 and 5 is in R, then 5 and 1 should not be in R, and so on. But for example, if 2 and 2 is in R, well, then that's okay, because 2 and 2 is in R. And so see, when you say 2 and 2, so let's say if this is your A, This is your A, this is your B. So then B and A will be also 2 and 2, right? So then A and B is in R, B and A is also in R. Then, so can we say that we don't have an antisymmetric relation? No, because here A and B are equal. So we have no problem with A and B and A, both of them in R, right? So, but if you want to have an antisymmetric relation and the two elements are different, then if one of them is in the relation, the other one cannot be in the relation. So if 1 and 2 is in the relation, 2 and 1 cannot be in the relation. Or if 2 and 1 is in the relation, then 1 and 2 cannot be in the relation, because 1 and 2 are different elements. But if the elements are the same, for example, 2 and 2, yes, 2 and 2 and 2 and 2 both are in the relation, but 2 is equal to 2. So we don't have an issue with that. So 2 and 2 being in the relation doesn't mean anything. Doesn't mean that the relation is symmetric or doesn't mean it's antisymmetric. None of them. So we just don't care about 2 and 2. We care about the elements A and B, where A and B are different. Okay, so that's one important point, that for symmetric and antisymmetric relations, you have to look at the elements that are, or the pairs whose coordinates are distinct or different. If A and B implies B and A, if A and B in R implies B and A in R. So for example, if you have a relation that 1 and 2 is in there and 2 and 1 is there, also 5 and 1 is there and 1 and 5 is in there. So whenever A and B is in there, then B and A is in there, then you have symmetric. But if you have a relation that whenever 1 and 5 is there, for example, 5 and 1 is not there, or 2 and 1 is there, 1 and 2 is not there, then you have antisymmetric. But if you have a relation that sometimes A and B, for some A and B's, B and A's are there, for some A and B's, B and A's are not there. So for example, 1 and 2 and 2 and 1 are both there, but 1 and 3 is there, but 3 and 1 is not there. So sometimes this, sometimes that. Then we have a relation which is neither symmetric nor antisymmetric. Okay, so it is definitely possible to have a relation which is neither symmetric nor antisymmetric. So I'm going to give examples for all of these, but let me first finish the definitions, okay? And then I'll just explain about this definition a little, but I'm going to give the examples as well. So next definition. So we did the definition of symmetric and antisymmetric. Transitive, a relation R on a set A is called transitive if whenever A and B is in R and B and C is in R, then A and C is in R. Okay, so transitive means whenever A and B and C both in R, then A and C is in R as well. All right, so let's look at an example here. Let A equals Z and define the relation R as follows. A R B if A is less than equal to B. So part A is R reflexive. So we define the reflexive relations and symmetric, antisymmetric, and transitive. Is R reflexive? So what is the definition? Whenever you want to answer a question in mathematics, you have to look at the definition. What is the definition of reflexive? So let's look. We said a relation is reflexive if A and A is in R for every A in A. So my A here, my capital A here is Z. So can I say that A and A is in R for every A in Z. So I have to again look at the definition of relation. When can I say that A and A is in R? If A is less than or equal to A. Because according to the definition, A and B is in R if A is less than or equal to B. Now, if I fix my element A in Z, can I say that A and A is in R? Yes. Why? Because A is less than or equal to A, right? For every A is less than or equal to A. Therefore, for every A comma A is in R, which means my relation is reflexive. So this is, let me say one more time that the meaning of this is A and B is in R if A is less than or equal to B. Okay, so this is just another notation for this sentence. So if you're more comfortable with this type of sentence, you can write down this type of sentence, but in the exam, I may give you this type of sentence or this type of sentence, but they have the same meaning. It's just another notation. So the answer is yes. Let A in Z be an arbitrary element, right? Because we have to show that for every element A in Z, A comma A is in R, an arbitrary element. Then A comma A is in Z, sorry, is in R, since A is less than or equal to A. Thus, A comma A is in R for every A in Z. So that means R is reflexive. Part B, is R symmetric? Symmetric means what? Again, let's look at the definition. Symmetric means whenever A and B is in R, then B and A must be also in R. So let's suppose that A and B is in R. So suppose that A and B is in R, i.e. A is less than or equal to B. So can we conclude B and A is in R, i.e. can we conclude that B is less than or equal to A? If the answer is yes, you have to prove in general. If the answer is no, give a counterexample. The answer is no. Charge the pencil. The answer is no. Counterexample. 2 is less than or equal to 5. So therefore 2 and 5 is in R, but 5 and 2 is not in R, since 5 is not less than or equal to 2. 2 and 5 is in R. Remember, A and B is in R if A is less than or equal to B for this type of relation, according to the definition given in the question. So 2 and 5 is in R because 2 is less than or equal to 5, but 5 and 2 is not in R because 5 is not less than or equal to 2. So another, let's say part C, is R antisymmetric? So antisymmetric means what? Means if A and B is in R, and B and A is in R, can we conclude A equals B? If the answer is yes, this is a definition of antisymmetry. If A and B is in R and B and A is in R, then A must be equal to B. Can we say this is true? Yes. If A and B is in R, then A is less than or equal to B. If B and A is in R, then B is less than or equal to A. And if A is less than or equal to B, and B is less than or equal to B, and A is less than or equal to B, and B is less than or equal to A, then we can conclude that A is equal to B. That's just a simple property of inequalities. If A is less than or equal to B and B is less than or equal to A, then A equals B. So the relation is antisymmetric. And part D is R transitive. The answer is, so let's see, if A and B transitive definition of transitive relation is if A and B belongs to R and B and C belongs to R, can we conclude A and C belongs to R? A and B is in R and B and C is in R, then can we say A and C is in R? The answer is yes. If A and B is in R, then we can say that A is less than or equal to B. If B and C is in R, then we can say B is less than or equal to C. So these two together means A is less than or equal to C by a property of inequalities. And therefore we can say that A and C belongs to R. If A is less than or equal to C, then A and C belongs to R. Okay, so the answer was yes. If A and B and B and C are in R, then A and C is in R. So therefore this relation is transitive, reflexive, antisymmetric, but it's not symmetric.